Hello everybody and welcome to this short tutorial on RF and microwave measurements. My name is Erikos Lourandakis and my passion on microwave measurement techniques and equipment comes from my background as a microwave engineer and lab administrator both in academia and industry. You can find more information on this material at my homepage lourandakis.com. From my professional background, I'm dealing a lot with electromagnetic modeling and characterization of silicon devices. Over the last years, I've served as an administrator for a silicon characterization lab. The main measurement equipment include a semi-automatic probe station and a two-port network analyzer up to 70 GHz. The material presented in this tutorial is addressing some basic principles of network analyzer measurements and de-embedding. The outline of this presentation is given here. First, we will mention briefly the properties of linear and nonlinear networks. Following is an introduction to the vector network analyzer basics. Scattering parameters, also called S-parameters, are then introduced as the basic measurements for linear networks. The error model associated with network analyzer measurements and the basics of calibration theory are discussed next. Calibration standards and their properties are presented as used in the calibration process with a network analyzer. And finally, de-embedding of feed lines is discussed based on a PCB design example. Let's begin with some basic principles of microwave network theory. There are two major network types, namely linear and nonlinear networks. For linear networks, the input and output frequencies are identical. The output signal simply undergoes amplitude and phase change. Linear networks can be characterized by their S-parameters, as measured with a network analyzer. On the other hand, nonlinear networks may have a very distorted output spectrum. Multiple harmonics and mixing products may be present at the output terminal of the device under test. In this case, small signal network analysis, as described by S-parameters, is no longer valid. Let's have a closer look at the linear network theory by considering two-port networks. A sinus wave of certain frequency f0 passed through such a network will be present at its output with the same frequency, having a phase shift in respect to the input and an altered amplitude. The incident wave at the input port of the network is partially reflected and transmitted to the output port. Linear networks are described in terms of reflection and transmission parameters. Reflection parameters are calculated from the ratio of reflected to incident power. Transmission parameters are calculated from the ratio of transmitted to incident power, respectively. These network parameters can be measured with a network analyzer in the form of S-parameters. The vector network analyzer is a measurement system for capturing complex network parameters for both reflection and transmission. For doing so, the network analyzer has a built-in frequency synthesizer that generates the sinus wave that is swept over the bandwidth of interest. At each frequency point, the reflection and transmission parameters are measured at both analyzer ports. In the forward direction, the internal source is switched to analyzer port 1, while port 2 is terminated with 50 ohms. The incident wave is passed through the bidirectional coupler to port 1 and detected at reference receiver R1. The portion of the incident wave that is reflected from the DUT is passed through the bidirectional coupler to receiver A. Now, from the ratio of reflected to incident wave, the reflection parameter S11 is calculated. The transmitted wave that passes through the DUT is coupled out by the bidirectional coupler at port 2 and detected at receiver B. Now, from the ratio of transmitted to incident power, the transmission parameter S21 is calculated. On the other hand, in the reverse direction, the internal source is switched to port 2, while port 1 is terminated again with 50 ohms. In the same way as before, the reflection parameters S22 and transmission parameters S12 are now calculated at each frequency point. The S parameter measurement is now completed at both analyzer ports. Calibration is an important link in the chain of network analyzer measurements. By definition, calibration is a mathematical procedure of removing imperfections in the test system. The calibration routine is always performed prior to the actual measurement of the device under test. The types of errors associated with network analyzer measurements can be classified as systematic, random, and drift errors. Systematic errors are due to hardware limitations of the network analyzer itself, such as coupler directivity and impedance mismatch at the load and source terminals. These errors are systematic and can be removed by calibration. Random errors, on the other hand, cannot be removed since they are not constant over time. Main sources of random errors are instrument phase noise and switch repeatability. Finally, drift errors are due to instrument performance variation after the calibration, for example, due to temperature drift. These errors can be removed by a new calibration. Let's proceed with a discussion of the error models associated with network analyzers. Errors introduced by the measurement setup, for example, the coaxial cables and connectors that are introduced between the network analyzer and the DUT, have to be removed by the calibration. For doing so, a fictitious error adapter is considered between the DUT and the reflectometer of the VNA. This error adapter contains terms for the forward and reverse direction. The error terms are then calculated by measuring well-defined calibration standards at each step of the calibration process. In the forward operation, the measurement setup is described by the flow graph shown here, which yields the measured parameters S11M and S21M. These two equations contain all 4 actual S parameters of the DUT and the 6 forward error terms. These error terms are addressing the directivity, port 1 matching, reflection tracking, transmission tracking, port 2 matching, and leakage. The individual error terms are calculated automatically by measuring the appropriate calibration standards. In the reverse operation, the source and load terminals have been switched. The resulting new flow graph is shown here, which allows for measuring the parameters S22M and S12M. Again, these two equations include the S parameters of the actual DUT and the 6 reverse error terms. Combining the forward and reverse equations with the calculated 12 error terms results in the extraction of the actual DUT S parameters. In practice, the calibration routine is performed before the actual DUT measurement. A VNA calibration consists of several steps which are summarized here. The operator is prompted to connect open, short, and load standards at both network analyzer ports. Finally, a through is inserted between the two analyzer ports. At each calibration step, the corresponding error terms are calculated by measuring the well-defined calibration standards. After the applied corrections, the reference plane of the test system has been moved to the center pin at the end of the coaxial cable. At this point, we are ready to insert the DUT and perform the actual measurement. As we have seen so far, calibration standards play a crucial role in network analyzer measurements. A widely used calibration routine is called SOLT and has its name from the use standards short, open, load, through. An ideal open or short would have perfect signal reflection. In reality, the open has a parasitic fringe capacitance between signal and ground, and the short has an inductance between the two terminals. An ideal load would be a perfect termination resulting in zero reflection. Real-world load standards have an impedance which is frequency dependent. An ideal through would have zero loss and electrical length. In reality, a through standard has some insertion loss and phase shift due to its physical length. To put it in simple words, there are no ideal cal standards, and that's why we need well-defined standards for a quality calibration. An open standard makes no connection between the signal and ground terminals and ideally reflects the incident signal with no loss. An ideal open would result in a reflection coefficient gamma equals 1 and 0 degrees phase shift. In reality, the electric field travels from signal to ground by forming a parasitic capacitance which can be described by a polynomial. The coefficients of this frequency-dependent polynomial are entered into the network analyzer when defining the open calibration standard. As a result of the parasitic capacitance, we witness the reflection parameter S11 moving clockwise along the low part of the Smith chart as frequency increases. An ideal short totally reflects the incident signal with no loss and results in a reflection coefficient gamma equals 1 and a phase shift of 180 degrees. In reality, all short standards have some parasitic inductance since the short is implemented as a metal trace between signal and ground terminals. The short inductance is described by a frequency-dependent polynomial, and its coefficients are then inserted into the VNA when defining the short calibration standard. This inductance is seen in the reflection coefficient S11, which moves clockwise along the upper part of the Smith chart as frequency increases. The simplest load standard is a terminating resistor between signal and ground with an impedance that matches the system impedance Z0, typically 50 ohm. Ideally, the load would have a flat impedance over the entire band of interest. In reality, some parasitic inductance is present in the leads between the terminals and the resistor itself. Additionally, some parasitic capacitance between the terminal exists. Looking at the reflection parameter S11 of a load standard, we get a trace that moves around the Smith chart center between the capacitive and inductive impedance regions. An ideal through connects the network analyzer port terminals with no loss and phase shift. The typical through realization is a matched transmission line of certain length and characteristic impedance Z0 that matches the impedance of the test system. The physical properties of the transmission line are introducing some loss and delay for the signal traveling between the analyzer ports. In order to remove these unwanted effects, we have to insert the electrical length of the through when defining, in the network analyzer, the through calibration standard. As we mentioned before, after the calibration is completed, we are ready to perform the actual DUT measurement. As it is often the case, our device under test is a small passive or active circuit or module, which has to be mounted on a PCB with coaxial connectors and feed lines. These feed lines, although necessary for performing the physical measurement, are distorting the actual DUT performance by inserting some loss and phase shift. This unwanted contribution of the feed lines can be removed by another mathematical procedure known as de-embedding. The de-embedding can be performed directly by the network analyzer by inserting the S-parameters of the feed lines. After a successful de-embedding procedure, we get the original DUT S-parameters. Let's discuss this topic further by considering a simple filter design example. Our target is to design and characterize a low-pass filter prototype on a PCB. The design specifications for the low-pass filter are summarized here. Corner frequency 5 GHz, passband insertion loss 0.5 dB, and attenuation at the first harmonic greater than 30 dB. We decide to use a fifth-order Chebyshev filter that fulfills the mentioned specifications. Calculating the filter components, namely capacitors and inductors, is now an easy task by using well-known expressions from the microwave filter textbooks. Once we have chosen the substrate material and the dimensions of the transmission lines for achieving the desired characteristic impedance, we can proceed with a layout for the actual low-pass filter. Using surface mount devices, also called SMD devices, for the capacitors and inductors is a widely used technique for prototyping. The SMD components have a specific footprint for soldering, which has to be taken into account when dimensioning the pads on the PCB. It is good practice to choose substrate thickness and transmission line technology that result in characteristic impedance of 50 ohm with dimensions close to the SMD pads. By doing so, we avoid large layout discontinuities between transmission line and SMD components. Starting with the PCB layout, we can proceed with the simulation of the low-pass filter. Inserting the models for the SMD capacitors and inductors into the PCB model and performing an electromagnetic co-simulation will result in the S parameters of the PCB low-pass filter. Using only the SMD models without the microstrip lines will result in the original filter S parameters. By comparing the two sets of S parameters, we notice that the filter performance gets distorted. The microstrip lines at the filter input and output are inserting some loss and deteriorate the impedance matching. This is the reason why we want to de-embed them from the measurements or simulations. The de-embedding can be performed directly by the VNA or by post-processing of the measured raw S parameters. All we need for the de-embedding are the S parameters of the microstrip line used at the input and output terminals of the PCB. The S parameters of the line can be obtained either by measuring a new PCB which consists only by the microstrip line itself, or by performing an electromagnetic simulation of the line structure. The DUT S parameters are then obtained from the raw parameters by removing the contribution of the lines. For doing so, we use ABCD network parameters here. The final de-embedded parameters of the DUT are calculated by transforming back the ABCD matrix into S parameters. Applying now the discussed de-embedding procedure to our low-pass filter example and comparing the DUT low-pass with the performance of the PCB low-pass, we get the S parameter sets shown here. It is interesting to note that the two sets of curves match perfectly. We have demonstrated now that when performed carefully, the de-embedding procedure is a powerful tool when characterizing prototype microwave networks. At this point, we end the tutorial on RF and microwave measurements. I hope you found the material interesting, and if you have any questions, please feel free to contact me through the web at lourandakis.com or directly via email. Thank you for your attention.